Okay, so section 4.4 is basically one of those sections where they take some math and then they hide it under a bunch of words. So we call this obfuscation. So the main problem is to peel off the words and then and then figure out how to use the math that we know to solve the problem, to solve it. Okay. So we'll start off. We're just going to do a bunch of examples of this. So here are some problems from the homework. Number 9 is what number in this set. So the set of non-negative reals exceeds its cube by the greatest amount. Okay, what number exceeds its cube by the greatest amount? Of course, if you have a number that's pretty big, then is it going to exceed its cube? No, right? So this is only going to happen for numbers. We know, in fact, that this is going to happen between 0 and 1. Somewhere between 0 and 1, you're going to have between 0 and 1, you have numbers that exceed their cubes, right? Because when you cube numbers that are smaller than 1, then they shrink, right? And we're wondering which one exceeds the cube, right? Exceeds its cube by the greatest amount. Okay. So what function are we interested in? Right? What function are we interested in? We want to look at how much a number exceeds its cube, right? So what are we looking at? The number, right? So you have some number x, right? And we want to know how much bigger it is than its cube, right? So its cube is x cubed, right? And we look at the difference, right? Okay. This is by how much a number exceeds its cube. Let's call that thing f. Okay. And so we want to know for where this function is the largest, right? Where this function is greatest. And so what do we need to do? We need to take the derivative, right? So let's take this derivative, right? We get 1 minus 3x squared, right? And then what do we do? Set it equal to 0, right? So this 1 minus 3x squared equals 0 means that 1 equals 3x squared. X squared is equal to 1/3, right? So x is 1 over the square root of 3. Right? And if we want to check it, right? So we say, okay, here is, let's see, so let's say that this is 1 over the square root of 3. And what do we know about the values of this? I guess we also know that this would be 0 at negative 1 over the square root of 3. Right? And what do we know about this function? What do we know about the derivative f prime? About the signs of the derivative? So let's say between here and here, what is it? It's positive, right? It's positive, right? And then it's negative. It's negative out here, and it's negative over here. Not that that matters. Okay. Right. So what does that tell you? That tells you that the original function increases up until this point, and then decreases afterwards. Right. So that tells us that this candidate we knew that this is a possible place for an extrema, and now by using the first derivative test, we know that in fact this is a max. Right. So this is your critical point, right? And we know that, now we know that, in fact, 1 over root 3 is a local max. fact, we know it's so it's increasing and then it's decreasing. Okay, so it's a local max, and so that's right. That is the place where we have the biggest amount. Right? Okay. Any questions about that? Any questions about that? Okay, so this is it. I guess. How do you know it's a global max? How do you know it's a global max? Yeah, Rich?
Well, if it's for all x that is the max, then it would be global max. So I guess you can try to, I guess what you could do is between negative 1 over root 3 and 1 over root 3 to try to find if there's any like other value that exceeds the local max.
Say it one more time. I'm sorry, I didn't.
So basically,
Yeah. Mm-hmm.
I mean, you could track it and you could see if any other value exceeds the value of the local max, and if it does, then you know that it's not a global max.
Yeah, but how would you do that? Right. That's only the question, right?
Mm-hmm.
You want to know if it's a global max, but how do you do that? Tete.
There's only that the positive is only between negative 1 over root 3 and 1 over root 3. So
Mhm.
if there's the max is there and the rest is like L on the right side is negative, then that max should be the global max.
Yeah. Okay, that makes sense, right? You say, okay, well, look, the function is increasing, right? The function's increasing up to here, and then after that, it's always decreasing, right? So in fact, that basically tells you that this is a global max, right? Just by looking at the behavior of the derivative, right? This is the only, you have a function, right? Here's 1 over root 3, here's 1 over root 3, here's 0, goes onwards, right? And the function increases up until a certain point, and then after that point, it's always, so it's increasing here and it's decreasing here, so this has got to be the global max, and it's local and global. Okay. Here's another problem. You have a piece of you have a square paper or cardboard, and it's 20 centimeters by 20 centimeters, and you are going to make a box by cutting out squares from the corners, and then folding those edges up. Okay. So the question is, so it's you're going to end up with a box and with no top. Okay? And the question is, what should the size of the squares be to maximize the volume of the box? Okay, so does anyone have ideas of how to, what we should do? Yeah, Helen.
Would you make a function, so like before the function is x minus x cubed,
Mm-hmm.
so the function here be 20 minus 2x
20 minus 2x. 20 minus 2x
squared?
squared. Mm-hmm. Yeah, so you say, let's call this thing, let's call the side length of the box x, right? You say, okay, well, the volume is going to be some function of x. It's going to be, in fact, 20 minus 2x quantity squared. Okay. Wait, is that the box? That's just the area of the base. Right. So that's times x. Right. Times the height. Right. And then, what do we need to do? We'll differentiate it. What happens when we differentiate it? The product rule, thank you. So you get the first times the derivative of the second. What's the derivative of the second, Robert?
2, 20 minus 2x minus 2.
Negative 2?
Oh, yeah.
Right, so the first times the derivative of the second, right, plus the derivative of the first times the second. And so what does that work out to be? You have this negative 4x, you have 20 minus 2x, you have another 20 minus 2x squared. Right? Like that's a 2 and the negative 2. Right? And then, what do you do here? You can factor it. Right? So you say, let's factor out 20 minus 2x. We're left over with a minus 4x plus 20 minus 2x. See? Right? And so you get 10 minus x, and you have here negative 6x plus 20, right? Negative 6x plus 20. Okay. So you end up with this. So it's a parabola. It's an upwards going parabola, right? And it has it intersects. So this equals 0 when x equals 10, and x equals 10/3. So 10 intersects, right? And it's an upwards going parabola, so we know that it's negative here, positive here, positive here. Okay, so what does that tell you? That tells you that the volume, the volume is increasing up until this point, and then it decreases. It decreases afterwards. Right? Decreases up until 10, and we actually shouldn't go beyond 10. Right? We don't want our x to go beyond 10 because right, x is basically we can only go up to 10 for x for the squares, because otherwise we have no more cardboard. Oh yeah, you have a question?
I think I'm just confused about the slope. If it's a plus on the left-hand side, shouldn't your slope be going upwards? Like your parabola part? It's not a negative slope, you just drew on your...
So so this is b prime. Yeah.
Okay.
This is b prime, right? B prime is this thing here, right? This parabola, right? The parabola is 0 at this point, and it's 0 at this point. It's an upwards going parabola, so I know it's negative here, and positive here. Okay. So what does that tell me about v, right? What does that tell me about v? It tells me that v is increasing, decreasing, and then increasing here. Right? If I look at this function, right, it tells me that my original function is increasing and then decreasing and then increasing. Okay. Again, don't get confused between b prime and v. Right? This, you were probably saying something about the slope of b prime. Yeah, it's true. The slope of b prime is negative here, right? But this is b prime, which tells us about the slope of b. Yeah, that's people always do that. They get confused between they mix up these two things. Yeah. Ellen?
Do you know how to define the slope, or like if we have the negative between 0 and 10 there?
Between 0 and 10 we know it, actually.
So it would just be.
It's positive. It's
Okay,
positive.
so you know.
We know that in fact, between negative infinity and 10/3, it's positive.
Okay.
Right? And between here and here, it's negative. Between here and infinity, it's positive.
Okay.
Okay. I just put the 0 on because we're actually not gonna take any numbers less than 0,
Okay.
right? Because we don't have a bigger card word, unless you have some negative card word. Okay, straightforward, simple. Okay. Any questions? Okay, we'll do some harder ones. Okay, so number 25, you have a length of wire. Okay, length of wire. And I should say that every time I see this problem, I think of my old high school calculus teacher who was from Boone, North Carolina, and he would say, "Suppose you've got a wire." Suppose you've got a wire. And, some sassy kid would say, "A what?" He'd say, "A wire." Yeah. So whenever I see this word, that's what I hear. Okay, so suppose you have a length of wire, and you would like to, for some reason, you want to use that wire to make two shapes. So you plan to make a circle and a square. Yeah, I'm from North Carolina. I was born in North Carolina myself, but I've lost most of my accent. I wasn't born in the mountains of North Carolina. Question? There was a question. Yes. No.
I was saying that I was from Charlotte.
Oh, really? Okay. So yeah, I grew up in Charlotte till I was 8. Yeah. And then I was born in Winston-Salem. That's how I got my name, Winston.
Right.
Yeah. Yeah, but I've lost my North Carolina accent. Although if I go back to North Carolina, I get it back pretty fast. I'll tell you a story. People seem kind of dead. During my first year of teaching in graduate school, I was at the University of Chicago. I think it was it's my third year as a graduate student, and they allowed us to teach calculus courses on our own. After a few weeks, the administrator, who's in charge of all the graduate students, comes to me, and she puts her hand on my shoulder and she says, "Winston, I have to talk with you." A student came to me and he said that he has to switch out of your class because he cannot understand your accent. And so I said, and she said, I spoke with him and I said, I know Winston O, and he doesn't have an accent. And the student insisted. He said, no, he has a very strong Chinese accent. I can't understand what he's saying in class. And I was like, okay, let's see, I was born in North Carolina. Is it my North Carolina accent that's still hanging on at this time? And so she eventually, she let the student switch out of my class. Clearly, he had trouble understanding that. Yeah. Anyway, so later on, I heard somewhere that there's some study done by linguists that people's prejudices are actually strong enough that if you show somebody somebody who appears to be from, say, mainland China, and dub it over with native American speakers, native English speakers, English, then they sometimes will think that the person has an accent, and vice versa. If you have a very white person and dub it over with the Chinese person's English, they say that he has no accent. So there's some perception switch that's possible. Anyway. Okay, so back to the problem. So you have this wire, and you're going to cut it into two pieces. right? You're going to cut it into two pieces and use one piece for this and one piece for this. And the question is, how should you cut? How should one cut the wire to achieve a minimum total area? How should you cut the wire to achieve a minimum total area? Okay, and I'll let you try this one. Okay, so take 3 minutes, 2 or 3 minutes, and see if you can get anywhere.
Do you know the length of the wire, or is it just a?
The length of the wire is just some number, L. It's some fixed number, L.
Is it the area of the square, the circle?
The total area. So total area.
Okay.
You're going to break it into two pieces. The first, you're going to form a circle. The second, you're going to form a square. You'd like to do it in such a way that the area is as small as possible. Which
But is so basically the wires being used for the area, or is it being used to make?
you're going to take this and you're going to bend it into a circle. You're going to take this thing and you're going to bend it into a square.
Okay.
Can we get a hint?
What?
A hint?
A hint.
Yeah.
So here's the hint. Call this this.
Are we gonna need to use an implicit differentiation?
No.
So the x
The hint is, just you have to talk about something, right? So let's call this x, and then in that case, this is going to be O minus x. Right? In that case, what's the area? If the circumference, well, I can keep it. Yeah, go on.
But you only have two variables, L and x.
L is a constant. Right? L is a constant. The wire is not changing. The wire isn't changing. Okay. Let's try it. Same. So you've broken your wire into two pieces, x and minus x. You've taken the first one, and you made a circle out of it. You've taken the second one, and you made a square out of it. Right. So this is L minus x of 4. Right. Right. Okay. So this one is easy, right? Finding we want some function about the total area, right? The area is going to be depending on x. It's going to be like the area of the circle plus the area of the square. The area of the square is easy. It's just going to be L minus x over 4 quantity squared. Right? What about the area of the circle? Go ahead. Tell me how you got it.
Yeah, so I said x is equal to the circumference, which is 2, or pi, which is 2 pi.
Okay.
I didn't include r.
Okay.
And then you would solve for r.
Okay.
You get x over 2 pi. So that's how the radius. And then you use that to solve for the area, which is pi r squared.
Right.
Pi. X over 2 pi r squared.
X over 2 pi squared times pi. Right, so you end up with x squared over 4. Okay, great. Thanks. Right, so you use your knowledge from elementary school. X is the circumference, right? 2 pi r. And then you solve for r. R is x over 2 pi, right? And then the area is pi r squared, right? So that's pi r squared, and it turns into x squared over 4 pi. Any questions? Okay, so you get x squared over 4 pi plus L minus x over 4 quantity squared. Right. Take 1 minute. Take 1 minute and find the maximum, or find the minimum, or at least differentiate it. Okay, somebody tell me what to do. A of x is x squared over 4 pi plus L minus x, quantity squared over 16. Right. So what happens when you differentiate? Cynthia? Differentiate the first one. Right, x squared. What?
Sorry, let me make it out.
You're panicking.
Yeah.
Somebody who's not panicking. Michelle.
So it's 1 over 4 pi times 2 x.
Mm-hmm. Yeah, so you get 1 over 2 pi x, right? You get 2x, right? You get 2x over 4 pi. Right? And this is x over 2 pi, and then over here you get what? You get
So you get 1 over 8
1 over 8
times minus x times -1.
times negative 1, right? Minus negative 1, so let me write that as x minus L over 8. right? And then, you find some sort of common denominator, say, so you get 4x over 8 pi plus pi x minus pi l over 8 pi. Right. So you get 4 plus pi x minus pi l over 8 pi. Okay. And then, setting that equal to 0, you see that a pi is 0 when 4 plus pi x equals pi over pi l, so x is going to be pi over 4 plus pi times l. Right, so that's the place where pi over 4 plus pi times l, right? That's the place where the derivative is 0